Component Object Model is a binary interface standard for software components introduced by Microsoft in 1993. It is used to enable inter-process communication and dynamic object creation in a large range of programming languages. COM is the basis for several other Microsoft technologies and frameworks, including OLE Automation, ActiveX, COM+, DCOM, the Windows Shell, DirectX, and Windows Runtime. Overview: the essence of COM is a language-neutral way of implementing objects that can be used in environments different from the one in which they were created, even across machine boundaries. For well-authored components, COM allows reuse of objects with no knowledge of their internal implementation, as it forces component implementers to provide well-defined interfaces that are separated from the implementation. The different allocation semantics of languages are accommodated by making objects responsible for their own creation and destruction through reference counting. Casting between different interfaces of an object is achieved through the query interface method. The preferred method of inheritance within COM is the creation of sub-objects to which method calls are delegated. COM is an interface technology defined and implemented as standard only on Microsoft Windows and Apple's Core Foundation 1.3 and later plug-in API, that in any case implement only a subset of the whole COM interface. For some applications, COM has been replaced at least to some extent by the Microsoft .NET framework, and support for web services through the Windows Communication Foundation. However, COM objects can be used with all .NET languages through .NET COM interop. Network DCOM uses binary proprietary formats, while WCF encourages the use of XML-based SOAP messaging. COM is very similar to other component software interface technologies, such as CORBA and JavaBeans, although each has its own strengths and weaknesses. Unlike C++, COM provides a stable ABI that does not change between compiler releases. This makes COM interfaces attractive for object-oriented C++ libraries that are to be used by clients compiled using different compiler versions. History: one of the first methods of inter-process communication in Windows was dynamic data exchange, first introduced in 1987, that allowed sending and receiving messages in so-called conversations between applications. Anthony Williams, one of the most notable thinkers involved in the creation of the COM architecture, later distributed two internal papers in Microsoft that embraced the concept of software components, object architecture, dealing with the unknown or a Euro-type safety in a dynamically extensible class library in 1988, and on inheritance, what it means and how to use it in 1990. These provided the foundation of many of the ideas behind COM. Object linking and embedding, Microsoft's first object-based framework, was built on top of DDE and designed specifically for compound documents. It was introduced with Word for Windows and Excel in 1991, and was later included with Windows, starting with version 3.1 in 1992. An example of a compound document is a spreadsheet embedded in a Word for Windows document. As changes are made to the spreadsheet within Excel, they appear automatically inside the Word document. In 1991, Microsoft introduced Visual Basic extensions with Visual Basic 1.0. A VBX is a packaged extension in the form of a dynamic link library that allows objects to be graphically placed in a form and manipulated by properties and methods. These were later adapted for use by other languages such as Visual C++. In 1992, when version 3.1 of Windows was released, Microsoft released OLE 2 with its underlying object model. The COM application binary interface was the same as the MAPI-ABI, which was released in 1992. While OLE 1 was focused on compound documents, COM and OLE 2 were designed to address software components in general. Text conversations and Windows messages has proved not to be flexible enough to allow sharing application features in a robust and extensible way, so COM was created as a new foundation, and OLE changed to OLE 2. In 1994, OLE custom controls were introduced as the successor to VBX controls. At the same time, Microsoft stated that OLE 2 would just be known as OLE, and that OLE was no longer an acronym, but a name for all of the company's component technologies. In early 1996, Microsoft found a new use for OLE custom controls, expanding their web browser's capability to present content, renamed some parts of OLE relating to the Internet ActiveX, and gradually renamed all OLE technologies to ActiveX, except the compound document technology that was used in Microsoft Office. Later that year, DCOM was introduced as an answer to CORBA-related technologies. COM was the major software development platform for Windows and, as such, influenced development of a number of supporting technologies. COM Plus and DCOM, in order for Microsoft to provide developers with support for distributed transactions, resource pooling, disconnected applications, event publication and subscription, better memory and processor management, as well as to position Windows as an alternative to other enterprise-level operating systems, Microsoft introduced a technology called Microsoft Transaction Server on Windows NT4. With Windows 2000, that significant extension to COM was incorporated into the operating system and renamed COM Plus. At the same time, Microsoft de-emphasized DCOM as a separate entity. Components that made use of COM Plus services were handled more directly by the added layer of COM Plus, in particular by operating system support for interception. In the first release of MTS, interception was tacked on. Installing an MTS component would modify the Windows registry to call the MTS software, and not the component directly. Windows 2000 also revised the Component Services Control Panel application used to configure COM Plus components. An advantage of COM Plus was that it could be run in component farms. Instances of a component, if coded properly, could be pooled and reused by new calls to its initializing routine without unloading it from memory. Components could also be distributed. COM Plus and Microsoft Visual Studio provided tools to make it easy to generate client-side proxies, so although DCOM was used to make the remote call, it was easy to do for developers. COM Plus also introduced a subscriber-publisher event mechanism called COM Plus Events, and provided a new way of leveraging MSMQ with components called queued components. COM Plus events extend the COM Plus programming model to support late-bound events or method calls between the publisher or subscriber and the event system. .NET. Microsoft.NET provides means both to provide component technology, and to interact with COM Plus. NET provides wrappers to most of the commonly used COM controls. Microsoft.NET hides most detail from component creation and therefore eases development. Despite this, COM remains viable technology, providing high performance, powerful and low bandwidth consumption remoting and unparalleled stability due to its nearly 2 decades of improvement. Microsoft uses COM for modern operating system components like the ribbon control provided in Windows 7 and Windows 8, besides hundreds of other COM components in their standard installation. It is also ideal for script control of applications such as Office or Internet Explorer since it provides an interface for calling COM object methods from a script rather than requiring knowing the API at compile time. .NET can leverage COM Plus via the System Enterprise Services namespace, and several of the services that COM Plus provides have been duplicated in recent releases of .NET. For example, the System Transactions namespace in .NET provides the Transaction Scope class, which provides transaction management without resorting to COM Plus. Similarly, queued components can be replaced by Windows Communication Foundation with an MSMQ transport. There is limited support for backward compatibility. A COM object may be used in .NET by implementing a runtime callable wrapper. NET objects that conform to certain interface restrictions may be used in COM objects by calling a COM callable wrapper. From both the COM and .NET sides, objects using the other technology appear as native objects. See COM interop. WCF eases a number of COM's remote execution challenges. For instance, it allows objects to be transparently marshaled by value across process or machine boundaries more easily. Windows Runtime. Microsoft's new Windows Runtime programming and application model is essentially a COM-based API, although it relies on an enhanced COM. Because of its COM-like basis, Windows Runtime allows relatively easy interfacing from multiple languages, just as COM does, but it is essentially an unmanaged, Native API. The API definitions are, however, stored in WINMD files, which are encoded in ECMA 335 metadata format, the same format that .NET uses with a few modifications. This common metadata format allows for significantly less overhead than pinvoke when WinRT is invoked from .NET applications, and its syntax is much simpler. Security. COM and ActiveX components are run as native code on the user's machine, with no sandboxing. There are therefore few restrictions on what the code can do. The prior practice of embedding ActiveX components on web pages with Internet Explorer did therefore lead to problems with malware infections. Microsoft recognized the problem with ActiveX as far back as 1996 when Charles Fitzgerald said, "We never made the claim up front that ActiveX is intrinsically secure." Recent versions of Internet Explorer prompt the user before installing ActiveX controls, enabling the user to disallow installation of controls from sites that the user does not trust. The ActiveX controls are signed with digital signatures to guarantee their authenticity. It is also possible to disable ActiveX controls altogether, or to allow only a selected few. The transparent support for out-of-process COM servers still promotes software safety in terms of process isolation. This can be useful for decoupling subsystems of large application into separate processes. Process isolation limits state corruption in one process from negatively affecting the integrity of the other processes, since they only communicate through strictly defined interfaces. Thus, only the affected subsystem needs to be restarted in order to regain valid state. This is not the case for subsystems within the same process, where a rogue pointer in one subsystem can randomly corrupt other subsystems. Technical details. COM programmers build their software using COM-aware components. Different component types are identified by class IDs, which are globally unique identifiers. Each COM component exposes its functionality through one or more interfaces. The different interfaces supported by a component are distinguished from each other using interface IDs, which are GUIDs too. COM interfaces have bindings in several languages, such as C, C++, Visual Basic, Delphi, Python and several of the scripting languages implemented on the Windows platform. All access to components is done through the methods of the interfaces. This allows techniques such as interprocess, or even intercomputer programming. Interfaces. All COM components implement the OLE interface, which exposes methods for reference counting and type conversion. A custom OLE interface consists of a pointer to a virtual method table that contains a list of pointers to the functions that implement the functions declared in the interface, in the same order that they are declared in the interface. The in-process invocation overhead is therefore comparable to virtual method calls in C++. In addition to custom interfaces, COM also supports dispatch interfaces inheriting from a dispatch. Dispatch interfaces support late binding for OLE Automation. This allows dispatch interfaces to be natively accessed from a wider range of programming languages than custom interfaces. Classes. A COM class is a concrete implementation of one or more interfaces, and closely resembles classes in object-oriented programming languages. Classes are created based on their class ID or based on their programmatic identifier string. Like many object-oriented languages, COM provides a separation of interface from implementation. This distinction is especially strong in COM, where objects cannot be accessed directly, but only through its interfaces. COM also has support for multiple implementations of the same interface, so that clients at runtime can choose which implementation of an interface to instantiate. Interface definition language and type libraries. Type libraries contain metadata to represent COM types. These types are described using Microsoft Interface Definition Language. IDL files define object-oriented classes, interfaces, structures, enumerations and other user-defined types in a language-independent manner. IDL is similar in appearance to C++ declarations with some additional keywords such as interface, and library for defining interfaces and collections of classes. IDL also supports the use of bracketed attributes before declarations to provide additional information, such as interface GUIDs and the relationships between pointer parameters and length fields. IDL files are compiled by the MIDL compiler. For C++, the MIDL compiler generates a compiler-independent header file containing struct definitions to match the VTBLS of the declared interfaces and a C file containing declarations of the interface GUIDs. C++ source code for a proxy module can also be generated by the MIDL compiler. This proxy contains method stubs for converting COM calls into remote procedure calls to enable DCOM for out-of-process communication. IDL files can also be compiled by the MIDL compiler into a type library. TLB files contain binary metadata that can be processed by different language compilers and runtime environments to generate language-specific constructs to represent the COM types defined in the TLB. For C++, this will convert the TLB back to its IDL representation. COM is an object framework. Because COM is a runtime framework, types have to be individually identifiable and specifiable at runtime. To achieve this, globally unique identifiers are used. Each COM type has designated its own GUID for identification at runtime. In order for information on COM types to be accessible at both compile time and runtime, COM uses type libraries. It is through the effective use of type libraries that COM achieves its capabilities as a dynamic framework for the interaction of objects. Consider the following example COM class definition in an idler. The above code fragment declares a COM class named SUM-class which implements an interface named ISOM-interface. This is conceptually equivalent to defining the following C++ class, where ISOM-interface is a C++ pure virtual class. The IDL files containing COM interfaces and classes are compiled into type libraries files, which can later be parsed by clients at runtime to determine which interfaces an object supports, and invoke an object's interface methods. In C++, COM objects are instantiated with a co-create instance function that takes the class ID and interface ID as arguments. Instantiation of some class can be implemented as follows. In this example, the COM subsystem is used to obtain a pointer to an object that implements ISOM-interface, and COM class CLSID. Some classes particular implementation of this interface is required. Reference counting. All COM objects utilize reference counting to manage object lifetimes. The reference counts are controlled by the clients through the addref and release methods in the mandatory known interface that all COM objects implement. COM objects are then responsible for freeing their own memory when the reference count drops to 0. Certain languages provide automatic reference counting so that COM object developers need not explicitly maintain any internal reference counter in their source codes. In C++, a coder may either perform explicit reference counting or use smart pointers to automatically manage the reference counts. The following are guidelines for when to call addref and release on COM objects. Functions and methods that return interface references shall increment the reference count of the returned object before returning. Release must be called on an interface pointer before the pointer is overwritten or goes out of scope. If a copy is made on an interface reference pointer, addref should be called on that pointer. Addref and release must be called on the specific interface which is being referenced, since an object may implement per interface reference counts in order to allocate internal resources only for the interfaces which are being referenced. All reference count calls are not sent out to remote objects over the wire. A proxy keeps only one reference on the remote object and maintains its own local reference count. To simplify COM development, Microsoft introduced ATL for C++ developers. ATL provides for a higher-level COM development paradigm. It also shields COM client application developers from the need to directly maintain reference counting, by providing smart pointer objects. Other libraries and languages that are COM-aware include the Microsoft Foundation classes, the VC compiler COM support, VBSCRIPT, Visual Basic, ECMAScript and Ball and Delphi. Programming. COM is a language-agnostic binary standard that can be developed in any programming language capable of understanding and implementing its binary-defined data types and interfaces. COM implementations are responsible for entering and leaving the COM environment, instantiating and reference counting COM objects, querying objects for supported interfaces, as well as handling errors. The Microsoft Visual C++ compiler supports extensions to the C++ language referred to as C++ attributes. These extensions are designed to simplify COM development and remove much of the plumbing code required to implement COM servers in C++. Registry usage: in Windows, COM classes, interfaces and type libraries are listed by GUIDs in the registry, under HKEY classes /CLSID for classes and HKEY classes /interface for interfaces. COM libraries use the registry to locate either the correct local libraries for each COM object or the network location for a remote service. Registration-free COM: registration-free COM is a technology introduced with Windows XP that allows component object model components to store activation metadata and CLSID for the component without using the registry. Instead, the metadata and CLSIDs of the classes implemented in the component are declared in an assembly manifest, stored either as a resource in the executable or as a separate file installed with a component. This allows multiple versions of the same component to be installed in different directories, described by their own manifests, as well as XCOPY deployment. This technique has limited support for exe-com servers and cannot be used for system-wide components such as MDAC, MSXML, DirectX or Internet Explorer. During application loading, the Windows loader searches for the manifest. If it is present, the loader adds information from it to the activation context. When the COM class factory tries to instantiate a class, the activation context is first checked to see if an implementation for the CLSID can be found. Only if the lookup fails is the registry scanned. Processor network transparency: COM objects can be transparently instantiated and referenced from within the same process, across process boundaries, or remotely over the network. Out-of-process and remote objects use marshalling to serialize method calls and return values over process or network boundaries. This marshalling is invisible for the client, who accesses the object as if it were a local in-process object. Threading: in COM, threading is addressed through a concept known as apartments. All COM objects live in exactly one apartment, which might either be single-threaded or multi-threaded. There are three types of apartments in COM: single-threaded apartment, multi-threaded apartment, and thread-neutral apartment. Each apartment represents one mechanism whereby an object's internal state may be synchronized across multiple threads. A process can consist of multiple COM objects, some of which may use STA and others of which may use MTA. All threads accessing COM objects similarly live in one apartment. The choice of apartment for COM objects and threads are determined at runtime, and cannot be changed. Threads and objects which belong to the same apartment follow the same thread access rules. Method calls which are made inside the same apartment are therefore performed directly without any assistance from COM. Method calls made across apartments are achieved via marshalling. This requires the use of proxies and stubs. In addition to the above modes, COM servers can also specify the both apartment mode. In this mode, the server auto-selects STA or MTA at object creation to match the apartment type of the calling thread. This can be useful to avoid marshalling overhead when MTA servers are accessed by a STA thread. Criticisms: since COM has a fairly complex implementation, programmers can be distracted by some of the plumbing issues. Message pumping: when an STA is initialized, it creates a hidden window that is used for inter-apartment and inter-process message routing. This window must have its message queue regularly pumped. This construct is known as a message pump. On earlier versions of Windows, failure to do so could cause system-wide deadlocks. This problem is complicated by some Windows APIs that initialize COM as part of their implementation, which causes a leak of implementation details. Reference counting: reference counting within COM may cause problems if two or more objects are circularly referenced. The design of an application must take this into account so that objects are not left orphaned. Objects may also be left with active reference counts if the COM event sync model is used. Since the object that fires the event needs a reference to the object reacting to the event, the object's reference count will never reach 0. Reference cycles are typically broken using either out-of-band termination or split identities. In the out-of-band termination technique, an object exposes a method which, when called, forces it to drop its references to other objects, thereby breaking the cycle. In the split identity technique, a single implementation exposes two separate COM objects. This creates a weak reference between the COM objects, preventing a reference cycle. DLL hell, because in-process COM components are implemented in DLL files and registration only allows for a single version of a DLL per CLSID, they might in some situations be subject to the DLL hell effect. Registration-free COM capability eliminates this problem. See also, Portable Object Cross-Language Cross-Platform Object Model Definition, Distributed Component Object Model, extension making COM able to work in networks, Common Language Infrastructure Current.NET Cross-Language Cross-Platform Object Model, Windows Runtime, an application model, evolved version of COM targeting Windows 8. CORBA Common Object Request Broker Architecture, Open Cross-Language Cross-Platform Object Model, DBus Open Cross-Language Cross-Platform Object Model, KDE KPART KDE Component Framework, XPCOM Mozilla Applications Cross-Platform Component Object Model, Java Beans, Java Remote Method Invocation, Internet Communications Engine, Language Binding, Foreign Function Interface, Calling Convention, Name Angling, Application Programming Interface, API, Application Binary Interface, ABI, SWIG Open Source Automatic Interfaces Bindings Generator from many languages to other languages, References. HTTP, Developer Apple Comic Core Foundation CFPLUGN's Conceptual HTML %23 Apple Refuid /201160-1002910 BAJFDFFC. Plugins and Microsoft Euro Unregistered Trademark SCOM. Apple Incorporated. Retrieved October 5, 2010. Microsoft Forum. Binary compatibility across Visual C++ versions, runtime callable wrapper a Euro MSDN library, COM callable wrapper a Euro MSDN library, HTTP, replay wayback Makino RG HTTP, www.java-world-COMJW03-1997/JW03 component web 97 HTML, HTTP, Docs Active State COM 2.4 HTML WIN32 COM DesignDex HTML, HTTP, www.body.org UK COM HTML, Compiler COM support. MSDN. Microsoft MSDN, C++ Attributes Reference, MSDN Magazine, C++ Attributes. Make COM programming a breeze with new feature in Visual Studio.NET, Assembly Manifests. MSDN. Retrieved November 5, 2009 ABC Dave Templin. Simplify app deployment with click once and registration-free COM. MSDN Magazine. Retrieved April 22, 2008 How to use an out-of-process COM server without its TLB file. Retrieved April 16, 2011 Concepts of Isolated Applications and Side-by-Side Assemblies. MSDN. Retrieved November 5, 2009 Microsoft MSDN, Processes, Threads, and Apartments, Microsoft MSDN, Single-Threaded Apartments, Microsoft MSDN, Multi-Threaded Apartments, Codagaru, Understanding COM Apartments, Microsoft MSDN, Understanding and Using COM Threading Models, COM, A Brief Introduction. Retrieved March 7, 2006 Box, Don. Essential COM. Addison Wesley. ISBN A0-201-63446-5 Chappell, David. Understanding ActiveX and OLE. Microsoft Press. ISBN A978-1-57231-216-6 Integration and Migration of COM+ Services to WCF. Retrieved April 15, 2010 External links: Microsoft COM Technologies, interview with Tony Williams, co-inventor of COM, a concise technical overview of COM from master's thesis, info, difference between OLE controls and ActiveX controls from Microsoft, type-lib data format specification with open source dumper utility. The COM/DCOM glossary.